Imagine staring into the night sky and seeing not just stars, but the faint glow of the universe's very first light, a whisper from 14 billion years ago, still lingering in the darkness. That's the cosmic microwave background, or CMB, the oldest light in existence. It's the afterglow of the Big Bang itself, a cosmic fingerprint imprinted on the fabric of space, carrying secrets from the moment everything began. This dim, almost imperceptible radiation blankets the entire universe, a relic so ancient it predates stars, galaxies, even atoms themselves. And yet, despite being one of the most studied phenomena in cosmology, it's teeming with mysteries that defy even our boldest theories. Scientists call the CMB the baby picture of the universe, a snapshot of its infancy frozen in time. But when we zoom in, this picture isn't as clear as we'd hoped. Tiny fluctuations in its temperature, strange patterns in its polarization, and anomalies that shouldn't exist according to our best models. All of these whisper questions we can't yet answer. Why do some parts of the CMB seem colder or hotter than they should be? What causes those eerie, large-scale asymmetries that challenge our understanding of the cosmos? And perhaps most unsettling of all, are these mysteries hinting at something beyond our current physics, something fundamental we've overlooked? This is where the real adventure begins. Because wrapped within that faint microwave glow are 25 unsolved enigmas, each one a puzzle piece that could rewrite our cosmic story. From the controversial axis of evil alignment to the perplexing lack of large-scale structure, these aren't just academic curiosities. They're clues pointing to gaps in our knowledge of dark matter, dark energy, even the very nature of space and time. Today, we're peeling back the layers of this ancient light, diving into the biggest questions that keep cosmologists awake at night. By the end, you'll see the universe not as a static backdrop, but as a dynamic, ever-evolving mystery, one where every answer leads to deeper, more thrilling questions. So let's step into the unknown together and uncover what the cosmos has been trying to tell us since the dawn of time. One of the most baffling puzzles hidden in the cosmic microwave background is something cosmologists call the horizon problem. Picture this: no matter which direction we look in the sky, the CMB's temperature is almost perfectly uniform, varying by less than 1 part in 100,000. At first glance, that might not sound strange, but here's the catch. Regions of the universe now billions of light years apart were once so far away from each other that, according to classical Big Bang physics, they could never have exchanged heat or information. They were beyond each other's cosmic horizons, forever out of reach. So how did these isolated patches of space end up with nearly identical temperatures? It's like walking into a room where 2 cups of coffee, brewed on opposite sides of the planet, somehow cooled to the exact same degree without ever being in contact. The leading solution to this puzzle is cosmic inflation, a theory proposing that the universe underwent a mind-boggling expansion in the first fraction of a second after the Big Bang. Imagine blowing up a balloon so rapidly that tiny wrinkles on its surface get stretched into near-perfect smoothness. Inflation would have done something similar, stretching space itself so quickly that any initial temperature differences were ironed out, leaving behind the astonishing uniformity we see today. But while inflation elegantly explains the horizon problem, it's not without its own mysteries. What triggered this hyper-expansion? Why did it stop? And perhaps most crucially, where's the definitive proof? Cosmologists point to subtle patterns in the CMB's polarization as potential fingerprints of inflation's gravitational waves, but the evidence remains tantalizingly indirect. Some researchers even argue that alternative theories, like varying speeds of light in the early universe, could explain the uniformity without invoking inflation at all. What's clear is this: the horizon problem isn't just a quirk of the CMB, it's a glaring clue that our understanding of the universe's earliest moments is incomplete. Solving it could mean rewriting physics itself, But if the cosmic microwave background's uniformity is puzzling, its anomalies are downright unsettling. Take the infamous cold spot, a mysterious region in the CMB roughly 1.8 billion light-years across, where the temperature drops just a bit lower than the surrounding glow. At first glance, it might not sound like much, just a faint chill in the cosmic sea, but this isn't some random fluctuation. The cold spot is so large and so cold that standard physics struggles to explain it. Statistically, it shouldn't exist. The odds of such a feature appearing naturally in our universe are less than 2%. So what's causing it? One leading theory suggests the cold spot could be a supervoid, an enormous, nearly empty bubble in space where matter is unusually sparse. In such a void, light passing through would lose energy as it climbs out of the gravitational well, a phenomenon called the integrated Sachs-Wolfe effect. Think of it like a cyclist pedaling uphill. The effort saps their speed. But here's the catch. While astronomers have found voids in the direction of the cold spot, none are large enough to fully account for the temperature drop. Either we're missing something colossal lurking in the shadows, or the void explanation falls short. Then there's the far more radical idea that the cold spot is evidence of a collision with another universe. If our cosmos is part of a multiverse where other bubble universes constantly form and expand, one of them might have brushed against ours in the distant past. The energy from that collision could have left a scar in the CMB, a cosmic bruise we now see as the cold spot. It's a breathtaking possibility, but also deeply controversial. Critics argue that such a theory leans too heavily on untested physics, with no way to independently verify it. The truth is, the cold spot defies easy answers. Some researchers even propose it could be a statistical fluke, a trick of the data amplified by our limited view of the universe. But if it's real and not just noise, this anomaly could be a window into something far stranger. Whether it's hidden voids, multiverse collisions, or entirely new physics, the cold spot reminds us that the universe still holds mysteries we're only beginning to unravel. Every time we think we've mapped the cosmos, it throws another curveball, and that's what makes the hunt so thrilling. If the cold spot challenges our expectations of randomness in the cosmos, the so-called axis of evil forces us to question something far more fundamental: the very assumption that the universe looks the same in all directions. Buried in the cosmic microwave background is a bizarre pattern that seems to align eerily with our solar system's plane, as if the universe has quietly tipped its hand. Scientists call this haunting alignment the axis of evil, not because it's malevolent, but because it undermines one of cosmology's bedrock principles, the cosmological principle. This foundational idea states that on large scales, the universe should be uniform and isotropic, no preferred directions, no special places, yet the CMB whispers otherwise. When researchers mapped the temperature fluctuations in the ancient light, they expected chaos, a splattering of hot and cold spots with no discernible order. Instead, they found something unsettling. The larger fluctuations appear oddly aligned along an axis that bizarrely coincides with the plane of our solar system. It's as if you shook a bucket of paint and the splatters formed a perfect arrow pointing back at you, the probability of this happening by pure chance. Less than 1 in 1,000. So is this a cosmic coincidence, or is there something deeper at play? Some argue it's just a fluke, an artifact of how we process CMB data, or an illusion created by our limited vantage point. After all, we're peering at the universe from inside a single solar system, and perhaps our local environment is casting a subtle shadow we don't fully understand. But others see a more radical possibility, that the axis of evil hints at a breakdown of the cosmological principle itself. Maybe the universe isn't as uniform as we thought. Maybe there's a preferred direction woven into the fabric of space-time, a relic of some exotic physics from the dawn of time. One controversial theory suggests the early universe might have rotated, imprinting a spiral-like structure on the CMB. Another proposes that our universe collided with another in the multiverse, leaving behind a telltale directional bias. The wildest idea that we're seeing evidence of a pre-Big Bang structure, an imprint from whatever existed before space-time as we know it began. Whatever the truth, the axis of evil forces us to confront an uncomfortable reality. The universe might not play by the rules we've written for it. Until we unravel this alignment's origins, it remains one of cosmology's most tantalizing loose threads, a quiet rebellion against the order we thought we understood. If the axis of evil makes us question the universe's uniformity, the missing large-scale anisotropies in the cosmic microwave background throw another wrench into our cosmological models. According to the standard lambda-cold dark matter, or lambdactum, framework, the reigning theory of cosmic evolution, the CMB should display a certain amount of variation, or power, in its fluctuations across vast distances. But when we zoom out to the grandest scale, something odd happens. The universe appears smoother than it should be, like a painting where the artist forgot to add broad brushstrokes, leaving large sections eerily blank. This so-called lack of power isn't just a minor discrepancy. It's a full-blown mystery that suggests our understanding of the early universe might be missing a crucial piece. Think of it like tuning into a radio station and hearing static where there should be music. The lambdactum model predicts a symphony of density fluctuations imprinted by quantum ripples from the Big Bang, but at the largest scales, the volume drops unexpectedly. The probabilities of this happening by random chance, less than 1 in 50. So what could be causing this cosmic hush? One possibility is that the universe is far stranger than our models account for. Some theorists propose exotic physics in the primordial cosmos, perhaps a phase of accelerated expansion before inflation, or a brief period where the laws of gravity behaved differently. Others suggest the answer lies in the geometry of spacetime itself. If the universe is finite but much larger than we can observe, or if it's shaped in an unexpected way like a hall of mirrors on a cosmic scale, it could suppress large-scale fluctuations in ways we haven't yet grasped. Then there's the unsettling chance that we're seeing the limits of lambdactum. For decades, this model has been the gold standard, explaining everything from galaxy clusters to the universe's accelerating expansion. But if it can't account for the missing anisotropies, we may need to rethink dark energy, dark matter, or even the nature of gravity itself. What makes this mystery so compelling is that it's not just about missing data, it's about missing expectations. The universe isn't just surprising us with what's there, it's surprising us with what isn't. And until we solve this puzzle, every cosmological model we build will carry a quiet asterisk, a reminder that the cosmos still has secrets it hasn't shared. Buried in the cosmic microwave background symphony of fluctuations is a peculiar silence, an unexpected hush in what scientists call the quadrupole moment. This feature, which describes how temperature variations stretch and compress across vast swaths of the sky, should theoretically ring out with a certain strength. Instead, it's oddly muted, like a musical note that's barely audible when it should be booming. The discrepancy isn't just a minor hiccup, it's a gaping hole in our understanding of the universe's structure, one that could rewrite the rules of cosmic topology or even hint at forces we've yet to discover. At the heart of the mystery lies the CMB's power spectrum, a cosmic fingerprint that charts the intensity of temperature variations across different angular scales. The quadrupole moment, representing patterns spanning about 90 degrees on the sky, is conspicuously faint compared to what our best models predict. Imagine expecting a thunderous drumbeat in a song but hearing only a faint tap instead. The odds of this happening randomly, less than 5%. So why is the universe holding back? One tantalizing possibility is that the cosmos isn't as infinite as we've assumed. If space folds back on itself in a finite, donut-like shape, a concept called compact topology, it could suppress large-scale fluctuations, including the quadrupole. Picture sound waves trapped in a small room. They can't resonate as fully as they would in an open field. Similarly, a wrap-around universe might mute the CMB's largest vibrations. While evidence for this idea remains speculative, it's a breathtaking reminder that the geometry of reality itself might be far stranger than we imagine. Then there's the wild card, primordial magnetic fields. These are hypothetical threads of magnetism woven into the fabric of the early universe long before stars or galaxies formed. If they existed, they could have tangled with the infant cosmos's plasma, subtly dampening the quadrupole's power. It's like stirring a pot of soup. The swirling motion changes how heat distributes. But here's the catch. We've never directly detected these ancient fields, and their existence would require physics beyond the standard model. The quadrupole anomaly isn't just a technical glitch, it's a cosmic riddle with existential stakes. If it points to a finite universe, it redefines the very stage on which everything plays out. If it's evidence of primordial magnetism, it could unlock secrets about the universe's first moments. Or perhaps it's a sign of something even more profound, an echo from before the Big Bang, a shadow of a cycle of universes we've yet to comprehend. Whatever the answer, this quiet discrepancy in the CMB reminds us that the universe still has volumes left to say. But the cosmic microwave background's defiance of randomness doesn't stop with the axis of evil. When scientists peer deeper into its statistical fingerprints, they uncover another layer of peculiarity, the octupole moment. This higher-order pattern in the CMB's temperature fluctuations should, like the quadrupole, be a chaotic splatter of hot and cold. Instead, it eerily echoes the axis of evil's alignment, as if the universe's blueprint contains hidden arrows pointing in the same direction. The odds of both the quadrupole and octupole moments lining up this way by chance, astronomically low. It's like rolling a pair of dice 100 times and getting snake eyes every single time something's clearly amiss. This conspiracy of alignment suggests the axis of evil might not be a fluke, but part of a broader cosmic mystery. One radical explanation: the early universe might have been spinning. Imagine a primordial gyroscope, its rotation imprinting a subtle directional bias on spacetime itself. If true, this would turn cosmology on its head. Our entire universe could carry the ghostly momentum of a spin dating back to the Big Bang. But here's the catch: a rotating universe would violate Einstein's assumption of isotropy, forcing us to rewrite the rules of relativity. Others argue the alignment could stem from something closer to home, an observational bias we've yet to untangle. Our solar system's motion through the cosmos creates a Doppler-like effect on the CMB, known as the kinematic dipole. Could this local motion be distorting our view of larger patterns? Some researchers suggest that incomplete subtraction of this dipole might leave residual alignments masquerading as cosmic anomalies. Yet even after meticulous corrections, the octupole's stubborn alignment persists, deepening the enigma. Then there's the multiverse angle. If our universe collided with another in its infancy, the shockwave could have carved preferred directions into the CMB's structure, leaving behind not just one but multiple aligned moments. It's a breathtaking idea, but without a way to probe beyond our cosmic horizon, it remains tantalizingly speculative. What makes the octupole moment so unsettling isn't just its defiance of randomness, it's the way it amplifies the axis of evil's challenge to our cosmic assumptions. Together, they form a pattern too precise to ignore, whispering that the universe might have a hidden architecture we're only beginning to glimpse. Whether it's primordial spins, unaccounted biases, or collisions with other realms, one thing's clear: the CMB's higher-order moments are holding up a mirror to our ignorance, reflecting questions we're just learning how to ask. Among the cosmic microwave background's many puzzles, few are as quietly disruptive as the whispers of non-Gaussianity, subtle deviations from the universe's expected statistical symphony. According to the standard cosmological playbook, the CMB's temperature fluctuations should follow a Gaussian distribution. a predictable bell curve of randomness where extreme highs and lows are rare and most variations cluster around an average. This smooth statistical fingerprint would match the gentle quantum ripples inflation stretched across the early cosmos. But when researchers comb through the data, they catch glimpses of something else, hints of clustering, asymmetries, or outliers that defy this tidy Gaussian expectation. It's as if the universe rolled its cosmic dice and just occasionally they landed stacked in impossible formations. These anomalies might seem like statistical noise at first glance, but their implications are profound. True Gaussian randomness would mean the CMB's fluctuations arose from simple, linear processes like the uniform crackling of a fire. Non-Gaussian signatures, though, suggest something more explosive, moments when the infant universe's physics went nonlinear, warping spacetime itself. One tantalizing culprit, primordial black holes, tiny, dense knots of matter that may have formed in the chaotic instants after the Big Bang. Picture a pot of boiling water. Most bubbles rise and pop in a predictable rhythm, but occasionally a violent surge sends droplets scattering wildly. Similarly, these black holes could have collapsed so abruptly that their gravitational shockwaves left twisted imprints on the CMB, disrupting its statistical purity. But there's an even wilder possibility: the fingerprints of other universes. In some multiverse theories, our cosmos isn't alone but floats in a vast quantum foam where other bubble universes constantly inflate and collide. If one of these neighboring realms brushed against ours in the first moments of time, the collision could have sent ripples through our CMB, leaving behind non-Gaussian scars. It's like hearing echoes in a cave, only the echoes are from a parallel reality's birth. Critics argue these anomalies might just be artifact systematic errors in how we process the CMB's faint signal, or foreground interference from our own galaxy's dust. Yet as measurements grow more precise, the deviations persist, nudging cosmologists toward a startling conclusion. The universe's randomness might not be so random after all. Whether it's primordial black holes, multiverse collisions, or physics we've yet to imagine, non-Gaussianity hints at a cosmos far more textured and far stranger than our theories predicted. And that's the real thrill. Every statistical outlier is a potential clue, a crack in the facade of our understanding where something extraordinary might be hiding. The cosmic microwave background should be the very definition of cosmic fairness, a uniform canvas of ancient light spread evenly across the sky. But when scientists mapped its power distribution, they stumbled upon something unsettling. One half of the universe appears subtly stronger than the other. This hemispherical power asymmetry isn't just a minor statistical blip, it's a full-fledged cosmic anomaly, with one hemisphere showing measurably more pronounced temperature fluctuations than its opposite. Imagine flipping a coin 1,000,000 times and consistently getting 60% heads. The universe, it seems, has a favorite side. At the heart of this mystery is a fundamental question. How could such an imbalance arise if the early cosmos was as smooth and homogeneous as inflation predicts? One leading theory points to primordial seeds, tiny density variations from the Big Bang that never fully evened out. Picture a pot of simmering soup with one side slightly saltier than the other. No matter how much you stir, traces of that initial unevenness linger. If certain regions of the infant universe contained faint overdensities, their gravitational pull might have amplified fluctuations in one direction, leaving behind the lopsided pattern we see today. But there's another, more provocative explanation. Our own motion may be distorting the cosmic snapshot. The Milky Way isn't sitting still. It's racing through space at over 600 kilometers per second, dragged along by the gravitational tug of distant superclusters. This movement creates a Doppler-like effect on the CMB, stretching light in the direction we're heading and compressing it behind us. While scientists carefully account for this kinematic dipole in their analyses, some argue residual effects might still skew the data, artificially amplifying one hemisphere's power. It's like trying to photograph a landscape from a speeding train. Even with corrections, the perspective might never be perfectly neutral. Yet the most mind-bending possibility is that the asymmetry isn't an illusion at all, but evidence of a deeper cosmic truth. Some models suggest the universe might have been born with an inherent gradient, a slight tilt in the laws of physics themselves. In this scenario, fundamental constants like the strength of gravity or the mass of particles could vary imperceptibly across space, leaving one half of the cosmos subtly different from the other. It's a radical idea, challenging the very notion that the universe plays by the same rules everywhere. The hemispherical power asymmetry forces us to confront an uncomfortable reality. The cosmos might not be as symmetrical as our theories demand. Whether it's primordial unevenness, unaccounted motion, or a fundamental breakdown of cosmological fairness, this imbalance is more than a curiosity. It's a clue that the universe's recipe might include ingredients we've yet to discover. And until we solve it, every map of the CMB will carry a quiet reminder. The sky, it seems, has a stronger hand to play. Dark matter should leave fingerprints all over the cosmic microwave background, its gravitational pull sculpting the CMB's fluctuations in ways we can predict with precision. Yet when scientists compare these pristine cosmic imprints to the signals claimed by underground dark matter detectors, something doesn't add up. The CMB suggests dark matter is cold, slow-moving, and omnipresent, while experiments like Xenon and LUX, designed to catch its elusive particles directly, keep coming up empty. It's as if the universe handed us two conflicting blueprints for the same invisible architect. So where's the disconnect? One possibility is that dark matter isn't what we've assumed. The standard candidate, weakly interacting massive particles, or WIMP, were long the darlings of cosmology. These heavy, sluggish particles fit neatly with the CMB's constraints, but decades of failed detections have forced a rethink. Enter actions, hypothetical particles so lightweight and ghostly they barely interact with ordinary matter. Unlike WIMP, which would leave explosive trails in detectors, actions could stream through Earth undetected, their presence only felt through their gravitational influence on the cosmos. Think of the difference between trying to catch a bowling ball in a net versus a whisper-thin veil of smoke. The CMB's tug of war with gravity could align perfectly with actions, while Earth-bound experiments built for WIMP might be blind to them entirely. But there's a more radical alternative. What if dark matter doesn't exist at all? Modified Newtonian dynamics, or MUND, proposes that our understanding of gravity is incomplete. Instead of invoking invisible matter, MUND suggests gravity strengthens subtly at ultra-low accelerations, like those found in the outskirts of galaxies. At first glance, this seems at odds with the CMB, which relies on dark matter's gravitational scaffolding to explain the universe's structure. Yet some theorists argue that certain relativistic extensions of MUND could mimic dark matter's effects on the CMB, fooling our measurements while sidestepping the need for undetectable particles. It's like realizing the shadow you thought was a lurking figure is just an odd-shaped branch. The truth may lie somewhere in between. Perhaps dark matter isn't a single entity but a mix of particles, actions, sterile neutrinos, even primordial black holes, each leaving distinct marks on the cosmos. Or maybe our experiments are missing something fundamental, like a hidden interaction that shields dark matter from detection. Whatever the answer, this discrepancy isn't just a technical hiccup. It's a rift between the universe as we see it and the universe as we touch it. And bridging that gap could redefine the very fabric of reality. The cosmic microwave background doesn't just map the universe's infancy, it also serves as a cosmic ledger, recording the precise amounts of ordinary matter, dark matter, and energy that filled the early cosmos. According to these pristine measurements, the density of baryons, the particles that make up atoms, should have set the stage for specific nuclear reactions in the first few minutes after the Big Bang. Those reactions, known as Big Bang nucleosynthesis, forged the lightest elements, hydrogen, helium, and trace amounts of lithium. But here's where the numbers stop adding up. While hydrogen and helium abundances match predictions spectacularly well, lithium is a glaring exception. The universe seems to have produced 3 times less lithium-7 than our models say it should have. This mismatch, known as the lithium problem, isn't just a minor accounting error. It's a crisis that forces us to question whether we've misunderstood nuclear physics, cosmology, or both. To grasp why lithium is such a thorn in cosmology's side, imagine baking a cake where every ingredient is measured to perfection, yet the finished dessert is missing half the sugar. The CMB tells us exactly how much flour and eggs, hydrogen and helium existed in the cosmic batter. But lithium, that subtle pinch of flavor, refuses to follow the recipe. The discrepancy is too large to dismiss as measurement error. Ancient stars, which formed from nearly pristine material, show lithium levels consistently lower than predicted, as if something in the early universe devoured lithium before it could accumulate. One camp of scientists argues the solution lies in nuclear physics. The rates of key reactions that produce lithium-7, like the fusion of helium-3 and helium-4, might be miscalculated in our labs. Subatomic interactions at extreme energies are fiendishly hard to replicate on Earth, and tiny errors could cascade into major abundance mismatches. It's like trying to predict the outcome of a high-speed collision by studying bumper cars. The scales don't quite match. Some theorists propose undiscovered quantum resonances or exotic particle interactions that could have suppressed lithium production, subtly altering the nuclear pathways in the universe's first moments. But others suspect the flaw isn't in our nuclear equations, it's in our cosmic assumptions. If dark matter particles interacted more strongly with ordinary matter than we thought, they could have disrupted nucleosynthesis, sapping energy from lithium-forming reactions. Picture a game of pool where invisible hands keep nudging the balls off course. Even stranger, certain modified gravity theories could tweak the expansion rate of the early universe, changing how long nuclear reactions had to cook before cooling halted them. A fraction of a second's difference might be all it takes to throw lithium off balance. The most radical solution may be the lithium never went missing, it just hid. Some stars might drag lithium down into their cores, burying it beneath layers where telescopes can't see. Or perhaps cosmic rays slamming into interstellar material gradually destroyed lithium over billions of years. But these explanations struggle to account for the sheer uniformity of the deficit across vastly different stellar environments. The lithium problem is more than a puzzle, it's a tension between 2 pillars of modern physics. If nuclear rates are at fault, it means our understanding of atomic nuclei is incomplete. If cosmology is to blame, it hints at dark matter's secrets or flaws in our Big Bang narrative. Either way, this tiny element carries cosmic weight, reminding us that even the smallest inconsistencies can upend our grandest theories. Until we solve it, the universe's ledger remains unbalanced, with lithium as its most stubborn outstanding debt. If the cosmic microwave background is our universe's baby picture, then the Hubble constant should be its birth certificate, a single number encoding how fast the cosmos is expanding today. But here's the problem. 2 of our most trusted methods for measuring this critical value disagree sharply, and the CMB is at the heart of the conflict. On one side, precise observations of the CMB's faint ripples suggest an expansion rate of around 67 kilometers per second per megaparsec. On the other, local measurements using pulsating stars and supernovas clock it closer to 73. This mismatch, dubbed the Hubble tension, isn't just a minor rounding error. It's a full-blown crisis that could mean our standard model of cosmology is missing a crucial ingredient. To understand why this gap matters, think of the Hubble constant as the universe's speedometer. The CMB gives us an indirect reading by extrapolating from the early cosmos's conditions. Like rewinding a video of an inflating balloon, we trace the universe's growth backward to deduce its current expansion rate. But local measurements take a more direct approach, using nearby celestial landmarks as mile markers. The fact that these methods disagree by nearly 10% isn't just embarrassing, it suggests something fundamental is wrong with our cosmic timeline. Either the early universe behaved differently than we thought, or our local observations are systematically flawed. One tantalizing solution lies in early dark energy, a hypothetical burst of repulsive gravity that might have surged briefly during the cosmos's first 100,000 years. This extra push could have subtly altered how sound waves traveled through the primordial plasma, tweaking the CMB's ripple patterns to mimic a slower modern expansion rate. Picture a car's odometer calibrated for smooth highways but unaware of a steep hill climbed early in the trip. Its final speed reading would be off. Early dark energy could be that hidden incline, invisibly skewing our CMB-based estimates. Yet skeptics argue the tension might stem from something more mundane, hidden errors in our local measurements. The cosmic distance ladder, a chain of techniques linking nearby stars to faraway galaxies, relies on a series of precarious assumptions. If even one rung is warped, like the brightness of certain supernovas or the geometry of stellar pulsations, the whole structure could lean toward a misleadingly high Hubble value. It's like measuring a room with a stretched tape measure. The numbers won't match the blueprint, but what if the truth is even stranger? Some theorists propose that dark matter interacts with itself in ways we've yet to detect, subtly reshaping cosmic structures over time. Others float the idea that our corner of the universe sits in a rare, underdense bubble, making local expansion appear unnaturally fast. These aren't wild guesses, they're desperate bids to reconcile a puzzle that defies our most trusted tools. The Hubble tension is more than a technical quarrel, it's a stark reminder that the universe still holds cards close to its chest. Whether it's unseen energy, measurement gaps, or entirely new physics, this discrepancy forces us to confront an exhilarating possibility. Our cosmic story might need a rewrite. And until we solve it, every calculation about the universe's age, fate, and composition carries an invisible asterisk, a whisper that something's amiss in the grand equation of everything. Dark energy is supposed to be the universe's most boring tenant, an unchanging, invisible force that's been accelerating cosmic expansion at a steady rate for billions of years. But what if it's not so constant after all? Lurking in the cosmic microwave background are faint whispers of something far stranger, phantom dark energy, a signal suggesting this mysterious force might be evolving, growing stronger or weaker over time. If true, this wouldn't just tweak our models, it would demolish one of cosmology's bedrock assumptions, forcing us to rewrite the story of the universe's fate. The evidence hinges on subtle distortions in the CMB's polarization patterns, imprinted when dark energy began dominating the cosmos around 5 billion years ago. According to the Standard Model, dark energy behaves like Einstein's cosmological constant, a static, immutable energy woven into spacetime itself. Yet some analyses of Planck satellite data reveal anomalies consistent with a dynamic dark energy, one that could have interacted with matter or even decayed since the Big Bang. Picture a river that's supposed to flow at a constant speed suddenly surging or slowing without warning. That's the level of cosmic upheaval we're talking about. Skeptics argue these signals are just noise artifacts of galactic dust or systematic errors in how we process the CMB's delicate fingerprints. After all, the anomalies are faint, hovering at the edge of statistical significance. But supporters counter that multiple independent studies, including cross-checks with large-scale galaxy surveys, have stumbled upon similar oddities. It's as if the universe keeps dropping the same cryptic hint, waiting for us to decipher it. The most tantalizing possibility, that dark energy isn't a constant at all, but a field that evolves according to unknown physics. Some theories propose it could be linked to quintessence, a dynamic energy field that changes density over time, like a cosmic breath inhaling and exhaling. Others suggest it might interact with dark matter, trading energy in ways that subtly alter the expansion rate. If either scenario is true, the implications are staggering. A strengthening dark energy could rip apart galaxies in a future big rip, while a fading one might allow gravity to regain control, collapsing the universe in a fiery crunch. Yet the real puzzle is why we're seeing these hints in the CMB at all. The cosmic microwave background freezes a snapshot of the universe at just 380,000 years old, long before dark energy should have left any measurable imprint. One radical explanation is that dark energy's roots stretch back to the primordial cosmos, influencing inflation or even triggering it. It's like finding a footprint in concrete that hardened millennia before the creature who made it could have existed. Whether phantom dark energy is real or just a cosmic mirage, its mere possibility underscores how little we understand the forces shaping our universe. The cosmological constant has been the simplest answer, but the CMB's murmurs suggest the truth might be far more complex and far more thrilling than we ever imagined. One of the most counterintuitive mysteries hidden in the cosmic microwave background revolves around a single number, omega. This parameter, representing the universe's total density, should, according to inflation theory, equal exactly 1, meaning space stretches perfectly flat like an infinite sheet. Yet when scientists parsed the Planck satellite CMB data, they stumbled upon a startling suggestion. Omega might be slightly greater than 1, hinting the cosmos curves back on itself like a 4-dimensional sphere. A closed universe, the statistical confidence was modest around 3 sigma, but the implications were staggering. If true, it would mean everything we thought we knew about cosmic geometry might be wrong. The controversy centers on gravitational lensing, an effect where the CMB's light subtly bends as it traverses the cosmic web of galaxies and dark matter. Planck's measurements of this lensing distortion appeared stronger than expected for a flat universe, as if spacetime itself were subtly warping the ancient light's path more than our models predicted. Picture shining a flashlight through a funhouse mirror. The way the beam bends reveals the mirror's curvature. Similarly, the CMB's distorted hotspots seem to trace the contours of a universe with positive curvature, one where parallel lines would eventually meet and the cosmos might even be finite. But here's where things get messy. Independent checks using baryon acoustic oscillations, frozen ripples in galaxy distributions, strongly favor a flat universe. So does the cosmic distance ladder. It's as if the CMB is whispering one story while every other cosmic messenger is shouting another. Some researchers argue Planck's anomaly stems from calibration quirks, tiny systematic errors in how the satellite subtracted foreground interference from our own galaxy's dust. Others suspect it's a statistical fluke, a fleeting outlier in the noisy data of cosmic history. Yet a small but vocal contingent insists the signal might be real. If so, the ramifications would rewrite cosmology. A closed universe could imply inflation didn't stretch spacetime as thoroughly as we thought, leaving behind residual curvature like wrinkles in an incompletely ironed sheet. Or perhaps dark energy behaves differently in a curved cosmos, its repulsive force sculpting expansion in ways we haven't accounted for, the wildest possibility. That we're seeing evidence of a pre-Big Bang topology, a relic shape from whatever existed before our universe began. The curvature controversy isn't just academic nitpicking, it's a battle over the universe's fundamental architecture. Until future missions like the Euclid telescope deliver more precise measurements, this discrepancy will linger like an unresolved chord in the symphony of cosmology, a reminder that even the geometry of reality itself isn't yet settled. Neutrinos are the universe's most elusive particles, nearly massless phantoms that stream through matter as if it weren't even there. For decades, physicists assumed they weighed nothing at all. Then came the shocking revelation. These cosmic ghosts do have mass, just so vanishingly small that weighing them became one of science's most delicate challenges. Yet here's where things get even stranger when we try to measure neutrino masses using particle experiments versus the cosmic microwave background. We hit a glaring inconsistency. The numbers refuse to match, and the discrepancy points to something profound lurking beneath the surface of our understanding. Particle accelerators and nuclear reactors peg the heaviest neutrino at around 2 electron volts, a feather's touch compared to even the lightest known particles. But the CMB tells a different story. By mapping how neutrinos subtly influenced the early universe's structure, Planck satellite data suggests their combined masses should be less than 12 electron volts, potentially much less. That sounds like a small gap, but in the subatomic world, it's a chasm. Either our lab experiments are missing something, or the cosmos is hiding neutrinos that behave unlike any we've seen before. One tantalizing possibility: sterile neutrinos, hypothetical cousins to the 3 known neutrino types that interact solely through gravity, making them invisible to all our detectors. If these shadowy particles exist, they could skew the CMB's neutrino mass estimates without leaving a trace in terrestrial experiments. Picture trying to weigh a bag of marbles while unseen hands keep adding or removing a few. Your measurements would never quite line up. Sterile neutrinos could be those phantom hands quietly tugging at the cosmic scales, but there's a wilder twist. Some theorists argue the mismatch hints at entirely new physics, perhaps neutrinos interacting with dark matter in ways that alter their apparent mass over cosmic time. Imagine pouring water into a leaky bucket. The longer it sits, the less remains. Similarly, if neutrinos decayed or morphed into other particles during the universe's infancy, their imprint on the CMB would differ from what we see in labs today. The stakes couldn't be higher. Neutrino masses are tied to some of physics' biggest mysteries, from why the universe has more matter than antimatter to the true nature of dark energy. Every decimal place in their measured weight could rewrite our models of particle physics and cosmology alike. And until we solve this puzzle, we're left with a haunting question. Are we missing a piece of the neutrino family, or is the universe playing by rules we've yet to discover? The cosmic microwave background doesn't just capture the universe's birth, it also holds clues to its turbulent adolescence. One of the most puzzling chapters in that story is reionization, the epoch when the first stars and galaxies flooded the cosmos with enough ultraviolet light to rip electrons from neutral hydrogen atoms, transforming the universe from an opaque fog into the transparent expanse we see today. According to the CMB's polarization patterns, this cosmic coming of age should have unfolded gradually, peaking around 500 million years after the Big Bang. But when astronomers point telescopes at the earliest known galaxies, they find something baffling. These ancient stellar factories seem too few, too dim, and too young to have done the job alone. It's like discovering a single candle was responsible for melting an entire glacier. The numbers just don't add up. This mismatch, known as the reionization paradox, forces us to reconsider some of our most basic assumptions about galaxy formation. The CMB's fingerprints suggest reionization was a slow, lumbering process, requiring a steady buildup of UV photons over hundreds of millions of years. Yet the galaxies we've spotted from that era appear late to the party, flickering to life only after reionization was already well underway. One possible resolution: hidden stars, vast populations of early dwarf galaxies too faint for our telescopes to detect. Picture trying to count campfires from an airplane. You might miss the countless tiny flames below the tree line. These overlooked galactic embers could have pumped out enough UV radiation to ionize the universe, their collective glow vanishing into the noise of cosmic background light. But there's a catch. Even if swarms of undiscovered dwarf galaxies exist, simulations struggle to explain how they formed quickly enough to match the CMB's timeline. Dark matter's gravitational pull should have acted like a cosmic brake, slowing the collapse of gas into stars early on. Some theorists propose radical fixes. Maybe dark matter was warmer in the early universe, its particles moving fast enough to smooth out small-scale clumps and accelerate galaxy birth. Others speculate about exotic astrophysical objects, super-energetic black holes, or annihilating dark matter particles that could have flooded the cosmos with ionizing radiation before stars took center stage. The most tantalizing clue lies in the CMB's odd polarization patterns, which hint at unexpected twists in reionization's plot. Certain large-scale swirls in the data suggest the process might have started in fits and bursts, with brief, intense waves of ionization crashing through the cosmic gas. It's as if the universe didn't just turn on the lights, it flickered the switch repeatedly, leaving behind a strobe-lit history we're only beginning to decode. Solving the reionization paradox isn't just about filling in a chapter of cosmic history. It's a test of whether we truly understand how the universe transitions from simplicity to complexity, from darkness to light. Every mismatch between the CMB story and the galaxies we observe forces us to ask, are we missing pieces of the puzzle, or is the puzzle itself more intricate than we ever imagined? Among the cosmic microwave background's most anticipated signals was supposed to be the faint swirls of B-mode polarization twisting patterns imprinted by primordial gravitational waves from the universe's first instance. These cosmic ripples, predicted by inflation theory, would have been the smoking gun for the explosive expansion that shaped the early cosmos. But when scientists peeled back the layers of the CMB's polarization data, they found something startling: silence. The B-modes were missing, or at least far weaker than expected. This absence isn't just a technical hiccup, it's a crisis for our understanding of inflation, forcing cosmologists to ask whether the universe's birth was quieter than we imagined, or if we're simply not listening carefully enough. The hunt for these primordial gravitational waves hinges on a key insight from Einstein. Violent spacetime ripples should leave twisting imprints on the CMB's polarization. Imagine throwing a pebble into a still pond. The circular waves that radiate outward are like the CMB's E-mode polarization, created by ordinary density fluctuations. But primordial gravitational waves should have sent out something wilder, spiraling disturbances like swirling eddies in that pond, leaving behind distinct B-mode curls in the ancient light. Detecting them would confirm inflation's most dramatic claim, that the universe underwent a split-second exponential expansion, magnifying quantum jitters into cosmic-scale ripples. Yet after years of painstaking observations, from ground-based telescopes like BICEP to space missions like Planck, the B-mode signal remains elusive. The most promising candidate, announced by BICEP-2 in 2014, turned out to be cosmic dust in our own galaxy, masquerading as primordial whispers. This null result has left theorists scrambling. Some argue inflation simply unfolded at lower energies than we assumed, producing gravitational waves too feeble for current detectors to spot. It's like expecting the roar of a jet engine, but hearing only the rustle of leaves. The mechanism might still be correct, just quieter. Others propose more radical solutions. Perhaps inflation wasn't a single, smooth event, but a stuttering process with multiple phases, diluting the gravitational wave signal. Or maybe the early universe's physics was fundamentally different, with exotic particles or extra dimensions suppressing spacetime ripples in ways we can't yet model. The most provocative idea, that inflation never happened at all, and alternatives like bouncing cosmologies or emergent universes could explain the CMB's smoothness without requiring a gravitational wave backdrop. But before we overhaul cosmology, there's a humbler possibility. Our instruments aren't yet sensitive enough. Future telescopes, like the Simons Observatory or Lightbird, will scan the sky with unprecedented precision, hunting for B-modes hidden beneath the noise. If they still find nothing, it won't just mean rewriting inflation, it could mean redefining how we think about the universe's first moments. The silence, after all, might be the most telling clue of all. Our universe is in motion, not just stars and galaxies, but the entire cosmic fabric itself. And one of the most fundamental clues to this grand drift comes from the cosmic microwave background's dipole anisotropy, a subtle but unmistakable signal that reveals our solar system's movement through the cosmos. At first glance, it seems straightforward. The CMB appears slightly hotter in the direction we're heading and cooler behind us, like the Doppler effect for light. But when scientists compare this motion to other cosmic reference frames, like the apparent flow of distant galaxy clusters, they hit a discrepancy that defies explanation. The numbers don't match, and that mismatch, known as the cosmic dipole anomaly, could mean everything from unseen superstructures tugging at us to cracks in Einstein's theory of relativity itself. Take the CMB dipole first. Measurements from satellites like Planck show our local group of galaxies barreling through space at roughly 630 kilometers per second relative to the CMB's rest frame. That's mind-bending speed, enough to cross the continental United States in under 7 seconds. But here's where things get strange. When astronomers map the bulk motion of galaxy clusters using techniques like the kinematic Sunyaev-Zeldovich effect, they find these distant structures seem to flow in a different direction, as if space itself is a river with conflicting currents. The misalignment isn't trivial. It's a 30-degree discrepancy that, statistically speaking, should be nearly impossible by chance. It's like setting sail by the stars only to discover your compass points somewhere else entirely. One tantalizing explanation: a vast, previously undetected mass, a cosmic attractor, lurking beyond our observational horizon. Picture the Shapley supercluster, an enormous wall of galaxies some 650 million light-years away, whose gravity pulls nearby galaxy groups toward it. Now imagine something even more massive farther out, tugging at the fabric of spacetime with enough force to skew not just galaxies but the CMB's reference frame itself. Such a structure wouldn't just rewrite our maps of the cosmos, it would challenge the cosmological principle, the bedrock assumption that matter is evenly distributed on the largest scales. But there's a more radical possibility. What if the anomaly isn't caused by hidden structures but by the breakdown of relativity on cosmic scales? Einstein's theory assumes the laws of physics hold uniformly everywhere, but some modified gravity models suggest subtle variations could emerge over vast distances. If spacetime behaves differently in different regions, like a stretchy fabric with uneven tension, it could warp our measurements of motion, making the CMB dipole and galaxy flows appear misaligned when they're actually responding to the same underlying drift. The stakes here are cosmic. If the dipole anomaly stems from unseen mass, it implies our observable universe is just a tiny speck in a far vaster, lumpier cosmos. If it hints at new physics, it could mean relativity, our most successful theory of gravity, needs a fundamental update. Either way, this quiet discrepancy in the CMB's motion isn't just a technical oddity. It's a compass needle quivering between two equally revolutionary futures. The question isn't just where we're moving, but whether the universe itself is playing by rules we've yet to uncover. Buried in the cosmic microwave background's delicate fingerprints is a subtle but powerful tool called the Alcock-Paksinski effect, a cosmic yardstick that lets scientists measure the universe's expansion history by observing how large-scale structures stretch and squeeze over time. The principle is elegant in theory. As light from distant galaxies travels through expanding space, the apparent shapes of galaxy clusters and voids should appear distorted in predictable ways, like a grid of dots on a balloon stretching unevenly as it inflates. These distortions encode secrets about dark energy's behavior, whether it's truly constant or evolving over cosmic history. But when researchers analyze CMB-derived maps of the universe's web-like structure, they find discrepancies that refuse to fit neatly into our models. Some regions stretch more than they should, others less, as if the cosmos itself can't decide how fast it wants to grow. The strangest part, these anomalies don't just challenge our understanding of dark energy, they also raise unsettling questions about whether we're misreading the cosmic tape measure entirely. One camp argues the oddities hint at dynamic dark energy, a force that grows stronger or weaker over billions of years. Imagine a car's cruise control subtly fluctuating, sometimes accelerating, sometimes coasting instead of holding steady. If true, it would mean the universe's fate could swing between a fiery, big rip or a slow, cold fade, depending on when and how dark energy's grip tightens. Yet skeptics counter that the anomalies might stem from something far more mundane, cosmic mirages created by our own observational blind spots. Galaxy surveys rely on redshift, the stretching of light as space expands, to estimate distances. But if pockets of the universe contain hidden clouds of dust or unexpected galactic motions, they could skew our measurements, tricking us into seeing phantom distortions. It's like trying to judge the shape of a mountain through fog. The haze itself might warp your perception, the most tantalizing and controversial possibility. That the Alcock-Paksinski anomalies aren't mirages at all, but evidence of inhomogeneous dark energy. Most models assume this mysterious force pervades space uniformly, like an invisible mist. But what if it's clumpy, pooling in certain regions like cosmic puddles? Such variations could twist spacetime unevenly, leaving behind the very distortions we're struggling to explain. Future surveys like DAISY and Euclid aim to settle the debate by mapping millions more galaxies with unprecedented precision. Until then, these cosmic inconsistencies serve as a humbling reminder. Even our sharpest tools for measuring the universe come with shadows of uncertainty. Among the cosmic microwave background's most unsettling riddles is a phenomenon so strange it sounds like science fiction: dark flow. Across the universe, clusters of galaxies appear to be streaming in the same direction at breathtaking speeds, up to 800 kilometers per second, as if pulled by some invisible force beyond the edge of our observable cosmos. This collective motion defies everything the standard lambda model predicts. According to our best theories, the universe's large-scale structure should distribute matter and motion evenly, like bubbles in a rising loaf of bread. But the CMB's kinematic signatures tell a different story, revealing a cosmic current that points toward something massive lurking in the shadows. The evidence comes from subtle distortions in the CMB's temperature patterns caused by the Sunyaev-Zeldovich effect. As galaxy clusters plow through space, their hot gas scatters CMB photons, leaving faint streaks in the ancient light like wakes behind speeding boats. When scientists analyzed hundreds of these clusters, they found an eerie consistency. Their motions weren't random but aligned along a mysterious axis, as if drawn toward a gravitational magnet on the far side of creation. The odds of this alignment happening by chance, less than 1 in 1,000. So what cosmic hand could be tugging at entire clusters like puppets on strings? One radical possibility is that dark flow traces scars from before the Big Bang. If our universe inherited unevenness from a pre-inflationary phase, perhaps a collision with another bubble universe, those primordial wrinkles might still be tugging matter in preferential directions. Picture a sheet of ice with hidden cracks beneath. Even as the surface expands, the fractures beneath guide how pressure distributes. Similarly, pre-inflationary inhomogeneities could have etched gravitational gradients into spacetime itself, steering galaxy clusters along invisible rails. But there's an even wilder explanation. The flow might be driven by something outside our universe entirely. Some multiverse theories suggest neighboring cosmic bubbles could exert gravitational influence across the membrane separating them. If true, dark flow might be the first observable evidence of a parallel universe brushing against ours, its mass warping our cosmos like a fingerprint pressed into glass. Skeptics counter that such ideas stretch physics beyond testability. but supporters point out that dark flow's scale spanning billions of light-years demands equally colossal causes. Of course, not everyone's convinced the flow is real. Critics argue it could be an artifact of incomplete data or local peculiar motions amplified by selection bias. Yet as surveys like eROSITA map more clusters with higher precision, the signal persists, whispering of a universe more interconnected and more mysterious than we ever imagined. Whether it's primordial fingerprints, extra-dimensional neighbors, or something beyond our current physics, dark flow challenges us to reconsider not just where we're going, but what might be waiting in the unseen depths beyond. The cosmic microwave background spectrum is nearly perfect, a pristine blackbody curve so smooth it earned Nobel Prizes for confirming the Big Bang. But perfection in science is often a red flag. Hidden within that flawless glow could be spectral distortions, tiny kinks or bumps in the CMB's energy distribution, each a potential smoking gun for violent events in the universe's infancy. These anomalies, known as mu and y distortions, are the equivalent of finding faint fingerprints on an ancient artifact, suggesting someone or something tampered with the cosmic crime seen long after the Big Bang's initial fireball faded. Mu distortions are the quieter of the two, subtle wiggles in the CMB spectrum caused by energy injections in the universe's first few 100,000 years. Picture a calm pond suddenly disturbed by a pebble. The ripples that follow are like mu distortions, evidence of a burst of energy that heated the primordial plasma before it could fully thermalize. What could have caused such disturbances? One tantalizing possibility is the annihilation of exotic dark matter particles, their violent deaths releasing energy into the early cosmos. Another is the decay of relic particles from grand unified theories, leftovers from physics operating at energies far beyond anything our colliders can reach. These distortions are whispers from a time before atoms, carrying secrets about forces and particles we've yet to discover. Then there are Y distortions, the louder cousins. These arise later, between 1 million and 1 billion years after the Big Bang, when the universe's structure was taking shape. As the first galaxies and quasars ignited, their intense radiation heated intervening gas through a process called Compton scattering. Think of sunlight warming a pool, but on a cosmic scale. Hot electrons in this gas bumped into CMB photons, giving them an energy boost that left a characteristic spectral bump. The twist, the amplitude of this signal doesn't quite match our simulations. Some regions of the sky show more Y distortion than expected, as if pockets of the early universe were heated by something beyond the usual suspects, perhaps primordial black holes evaporating in bursts of Hawking radiation, or dark matter interactions that left scorching marks on the cosmic backdrop. The hunt for these distortions is like tuning an antique radio, searching for faint signals buried under static. Ground-based experiments like the Primordial Inflation Explorer and future satellites like the Probe of Inflation and Cosmic Origins aim to catch these spectral wrinkles with unprecedented precision. But the real excitement lies in the outliers, the distortions that don't fit the standard stories. A detected mu distortion could reveal the mass of hypothetical dark matter particles, while an anomalous Y distortion might hint at previously unknown astrophysical phenomena or even modifications to gravity itself. What makes these spectral anomalies so compelling isn't just their potential to expose new physics, it's their sheer unpredictability. Unlike the CMB's temperature fluctuations, which follow well-trodden inflationary models, distortions are wild cards shaped by the universe's most chaotic and poorly understood epochs. Every deviation from the perfect blackbody is a breach in the cosmic firewall, a crack through which we might glimpse the universe's hidden machinery. And if history is any guide, the most profound discoveries often start as the faintest tremors in the data. Gravity should bend light predictably. This fundamental truth lies at the heart of Einstein's relativity. But when scientists examine how the cosmic microwave background's light warps as it passes through the universe's vast web of dark matter, they stumble upon a discrepancy that refuses to fade. The CMB's lensing signal, the subtle smearing of its ancient light by massive cosmic structures, appears slightly stronger than our best models predict. It's as if the universe's invisible scaffolding clumps differently than we've assumed, or worse, that gravity itself behaves unexpectedly across cosmic distances. This anomaly hinges on a phenomenon called weak gravitational lensing. As CMB photons travel for billions of years, their paths gently curve around galaxies and dark matter halos, distorting the background like a funhouse mirror. By mapping these distortions, cosmologists can reconstruct the distribution of matter between us and the CMB's surface of last scattering, effectively turning spacetime's warps into a three-dimensional blueprint of the cosmos. But here's the catch. The Planck satellite's lensing measurements suggest matter clusters more tightly than lambda-quantum simulations anticipate, amplifying the CMB's lensing signal by nearly 7%. That might sound trivial, but in the high-stakes world of precision cosmology, it's a glaring outlier. One explanation points to dark matter's hidden complexities. What if it's not entirely cold and sluggish, as standard models assume, but carries a faint warmth particles with just enough kinetic energy to smudge the universe's large-scale structure? Picture pouring syrup versus splashing water. The latter spreads thinner, altering how it coats a surface. Similarly, warm, dark matter would delay the collapse of small-scale clumps, subtly shifting where and how matter concentrates. Alternatively, dark matter might interact with itself via unknown forces, creating pressure that reshapes cosmic scaffolding like invisible hands molding clay. Yet an even more radical possibility lurks. Spacetime's curvature might not follow Einstein's rules perfectly. Modified gravity theories, like those that tweak relativity on vast scales, could enhance lensing effects without invoking extra dark matter. Think of it as discovering that a lens you thought was ground to one specification actually has an uncatalogued irregularity, bending light in ways the manual didn't account for. Some models propose gravity grows marginally stronger in regions of extreme low density, precisely where cosmic voids stretch between galaxy clusters. If true, this would warp CMB light more dramatically as it traverses these underdense deserts, boosting the observed lensing signal. Critics counter that systematic errors might be at play, perhaps foreground galaxies contaminating the CMB's pristine signal, or subtle biases in how we reconstruct lensing maps from noisy data. But as next-generation telescopes like the Vera-C, Rubin Observatory sharpen our view, the anomaly persists, gnawing at cosmology's foundations. Whether it's dark matter's secrets, gravity's flaws, or something entirely unforeseen, this lensing mismatch isn't just a statistical hiccup. It's a crack in the mirror through which we view the universe, hinting that our reflections of reality might still be warped by forces we've yet to name. The cosmic microwave background is supposed to be the ultimate cosmic constant, a snapshot of the universe's fiery birth, unchanging across billions of years. But what if it isn't? A handful of studies claim to have detected something startling. The CMB's temperature fluctuations might be shifting over time, as if the universe's oldest light carries a flicker no one expected. If true, this time-streaming effect would shatter one of cosmology's bedrock assumptions that the CMB is a static relic, frozen in time since the universe's first moments. The implications are dizzying. Either our instruments are playing tricks on us, or the cosmos is hiding a dynamism that rewrites the rules of physics itself. At the heart of this controversy are faint anomalies in decade-spanning CMB datasets. When researchers compared early satellite measurements like COBE with modern observations from Planck, certain regions of the sky appeared to show subtle temperature variations, shifts on the order of millionths of a degree, but statistically significant enough to raise eyebrows. It's as if someone had taken the universe's baby picture and subtly altered the contrast in patches, leaving behind a cosmic palimpsest. The most provocative claim comes from a 2020 analysis suggesting the CMB's dipole, the hot and cold poles created by our solar system's motion, might be slowly rotating as if the fabric of space itself is drifting like a slow-motion whirlpool. Skeptics argue these signals are almost certainly artifact systematic errors lurking in the data's noise. Satellite calibrations drift over time, foreground emissions from our galaxy evolve, and even the way we process raw measurements can introduce phantom trends. Imagine trying to detect the slow fading of a mural while standing on a swaying ladder. Every tremor in your stance could mimic the change you're hunting for. Critics point to similar controversies like the infamous axis of evil, where later analyses revealed instrumental quirks masquerading as cosmic anomalies. But for those who take the time streaming claims seriously, the explanations veer into radical territory. One possibility is that dark energy, the mysterious force accelerating cosmic expansion, isn't constant but evolving, subtly altering spacetime's geometry in ways that refract CMB light differently over eons. Picture a pane of glass gradually warping in the sun, bending passing light at new angles each year. Another theory invokes cosmic defects, topological wrinkles in spacetime left over from the universe's violent infancy. These defects, akin to cracks in frozen ice, might move or decay over time, casting shifting shadows on the CMB. The wildest hypothesis that we're seeing evidence of a multiverse's gravitational tides. If our universe floats in a higher dimensional sea alongside others, their gravitational pull might slowly torque our local spacetime, imparting a faint rotation to the CMB's dipole. It's like discovering your compass doesn't point north because an invisible magnet lies buried beyond the horizon. The stakes couldn't be higher. Confirming time streaming would mean the CMB isn't just a fossil, it's a living record, still responding to forces we've yet to imagine. Future missions like CMB S4 aim to settle the debate with unprecedented precision, scanning the sky for any hint of temporal whispering in the ancient light. Until then, this mystery lingers at the edge of credibility, a tantalizing wisp of evidence that the universe's past might not be as static as we thought, and its future far less predictable. The cosmic microwave background maps the universe's structure with astonishing precision, revealing not just dense galaxy clusters but also vast, empty regions called supervoids, cosmic bubbles where matter is sparser than the surrounding universe. These underdensities should leave distinct imprints on the CMB through a process called the integrated Sachs-Wolf effect. As light travels through these voids, it loses energy climbing out of their shallow gravitational wells, creating subtle cold spots in the ancient light. Yet when astronomers compare these CMB predictions to actual galaxy surveys, something's off. The supervoids we've observed are smaller and shallower than the lensing data suggests they should be. It's like expecting a network of gaping craters and finding only faint dimples instead, a discrepancy that forces us to question whether our models of voids, gravity, or even the nature of dark energy are missing something fundamental. One possible explanation lies in the physics of voids themselves. Standard cosmology treats these regions as near-empty expanses where matter slowly drains outward over billions of years. But simulations suggest supervoids might evolve differently. Their edges could be sharper, their interiors more turbulent, or their growth stunted by dark energy's accelerating push. Imagine blowing bubbles in syrup versus water. The thicker fluid resists expansion, leaving smaller, more structured cavities. If voids behave similarly, their weaker gravitational signatures might resolve the mismatch. Yet even the most sophisticated simulations struggle to reconcile the CMB's lensing signal with the voids we actually see, hinting that the truth might be stranger. Then there's the gravity angle. Einstein's theory predicts how light should bend around cosmic structures, but what if gravity behaves differently in the universe's emptiest regions? Modified gravity theories, like those that tweak relativity to explain dark energy, often predict enhanced effects in low-density environments. In such models, voids would warp spacetime more dramatically than standard physics allows, amplifying their CMB lensing signal without requiring the enormous underdensities we've failed to observe. Picture a trampoline sagging under a bowling ball that's normal gravity. Now imagine the same trampoline denting deeply even under a feather. That's the kind of anomaly modified gravity might explain. But the most tantalizing possibility is that dark energy isn't the uniform force we've assumed. If it clusters unevenly, pooling more densely in voids, its repulsive push could counteract gravity's pull in ways that alter the CMB's lensing patterns. Think of it as a cosmic game of tug-of-war where the rope's thickness varies along its length, the balance of forces shifts unpredictably. Future galaxy surveys like the Vera Rubin Observatory's LSST could settle the debate by mapping voids in unprecedented detail, revealing whether they're truly missing or just hiding in plain sight, disguised by physics we've yet to understand. What makes this mystery so compelling is its stakes. If voids defy expectations, it's not just a quirk of large-scale structure, it's a challenge to the rules governing the cosmos itself. Whether the answer lies in galactic astrophysics, rewritten gravity, or dark energy secrets, one thing's certain: the universe's emptiest places might hold the keys to its deepest truths. In the grand tapestry of the cosmos, one of the most fundamental assumptions is symmetry, the idea that the universe doesn't play favorites between left and right. But buried in the cosmic microwave background's polarization patterns are whispers that could upend this cosmic fairness. Tentative signals suggest the CMB might carry a subtle imbalance, a preference for one-handedness over the other, as if the universe itself has a dominant spin. This potential parity violation isn't just a quirk, it's a crack in the mirror of reality, hinting at physics beyond the standard model or even the presence of ghostly action-like fields threading through spacetime. The clues lie in how the CMB's light twists as it travels across the cosmos. Normally, gravitational lensing should scramble any primordial polarization patterns randomly, leaving no preferred orientation. Yet certain analyses of Planck satellite data reveal faint but persistent anomalies, a slight excess of curling, spiral-like patterns in the polarization that favor one rotational direction over another. It's like stirring a cup of tea and noticing the liquid consistently swirls clockwise, defying the odds of randomness. The statistical significance is still debated, hovering at around 2 to 3 sigma, not enough to declare a discovery but too intriguing to dismiss. If real, this asymmetry could mean the early universe wasn't as even-handed as we thought. One tantalizing explanation involves action's hypothetical ultra-light particles that could have permeated the infant cosmos. These elusive entities, often invoked as dark matter candidates, might have coupled to photons in the primordial plasma, imparting a chiral twist to the CMB's polarization as they decayed or interacted. Picture a vast cosmic wind blowing through the early universe, gently nudging light waves to rotate in a preferred direction. Action-like fields could have been that wind, leaving behind a faint but detectable bias in the CMB's fingerprints. But there's a catch: human bias. Before we rewrite physics, we must confront the possibility that these signals are measurement artifacts. Galactic dust, for instance, emits polarized light that can mimic parity-violating patterns. Even the way telescopes scan the sky could introduce subtle systematic errors, like a camera adding unintended blur to a photograph. The Planck team painstakingly corrected for these effects, but skeptics argue the residuals might still contaminate the data. Future missions, like the upcoming Lightbird satellite, aim to scrutinize these anomalies with even sharper precision, separating cosmic truth from instrumental noise. The implications of a confirmed parity violation would reverberate far beyond cosmology. Such an asymmetry could link to one of the universe's oldest puzzles: why matter dominates over antimatter. Certain grand unified theories predict that parity-breaking processes in the early cosmos could have tipped the scales, favoring the creation of particles over antiparticles. If the CMB's handedness is a relic of that epoch, it would be the first observational thread pulling us toward a deeper theory of everything, one where the universe's very structure encodes its own lopsided history. For now, these signals remain on the edge of detection, teasing us with their ambiguity. But that's the thrill of the hunt. The most profound discoveries often start as faint tremors in the data, anomalies that refuse to vanish under scrutiny. Whether it's actions, new forces, or something beyond our current imagination, the CMB's potential left-right asymmetry reminds us that the universe still holds twists we've yet to unravel. And in those twists, we might finally find the missing pieces of reality's puzzle. Among the wildest interpretations of the cosmic microwave background's anomalies is a theory that sounds like it's ripped from science fiction, that these faint inconsistencies could be glitches in the code of a simulated reality. The idea isn't new. Philosophers have toyed with the notion that our universe might be an artificial construct for centuries. But when you examine certain CMB anomalies through this lens, the coincidences get unsettlingly specific. Take the CMB's low quadrupole moment, for instance. The fact that the largest scale fluctuations in the ancient light are curiously muted could, in an extreme interpretation, resemble the kind of data compression artifacts you'd expect if the universe were rendered on a finite resolution grid. Picture a video game world where distant textures blur because the system can't process infinite detail. What if the universe's low-res patches are hiding in plain sight, etched into the CMB's farthest reaches? Then there's the infamous axis of evil, that eerie alignment of temperature fluctuations with our solar system's plane. In a simulated reality, this could be a breadcrumb left by the programmers, a coordinate system or reference frame accidentally baked into the cosmic background. Think of it like finding the watermark of a graphics engine in the corner of a digital painting. Even the CMB's statistical deviations from perfect randomness, like those faint whispers of non-Gaussianity, could mirror the subtle patterns you'd expect from algorithmic noise, the cosmic equivalent of a random number generator showing its seams. Of course, this isn't hard science. Mainstream cosmologists rightly dismiss the simulation hypothesis as unfalsifiable speculation, a fun thought experiment with no meaningful way to test it. But the curious overlap between certain CMB anomalies and what you'd expect to see in a constructed universe does force an intriguing question. If we were living in a simulation, what would its artifacts look like? The CMB, as the oldest and most universal dataset we have, might just be the place to search. The problem is separating cosmic coincidence from genuine evidence. The cold spot could be a rendering error or just a statistical fluke. The hemispherical power asymmetry might reflect a universe stitched together from separate processing nodes, or plain old primordial unevenness. Without a way to distinguish between natural physics and deliberate code, the simulation argument remains a philosophical rabbit hole. But here's the irony. The very act of studying the CMB's anomalies with such precision is itself a kind of cosmic debugging. Every time we map its imperfections, we're probing the universe's deepest operating system, whether it's natural or not. And that, perhaps, is the real takeaway. The CMB doesn't just illuminate the universe's past, it holds up a mirror to our own relentless drive to understand it, pixelated or otherwise. The cosmic microwave background has been called the universe's oldest postcard, a pristine message from the dawn of time. Yet, as we've seen, that postcard is scribbled with 25 unsolved riddles, each one a crack in the facade of our cosmic understanding. From the eerie cold spot to the rebellious axis of evil, from phantom dark energy to the whispering anomalies in primordial lithium, the CMB refuses to be just a relic. It's a living puzzle, one that dismantles our assumptions as fast as we build them. Every time we think we've decoded its secrets, it throws another curveball, forcing us to question whether we've misunderstood gravity, misjudged the universe's shape, or missed entire chapters of its history. What makes these mysteries so electrifying isn't just their complexity, it's their sheer audacity. The CMB's anomalies don't quietly nudge cosmology forward, they grab it by the collar and drag it toward revolution. To explain the horizon problem, we had to invent cosmic inflation, a theory so radical it reshaped our concept of time. To account for dark flow, we're flirting with multiverses and pre-Big Bang physics. Even the simplest discrepancies, like lithium's stubborn absence, threaten to upend nuclear astrophysics. The CMB isn't just a treasure map, it's a gauntlet thrown at the feet of every cosmologist, daring them to think bigger. And that's the thrilling part. We're not just filling in gaps anymore, we're hunting for entirely new physics. Maybe the answer lies in quantum gravity, where space-time itself fractures into foam. Maybe it's hidden in the holographic principle, where our three-dimensional universe is just a projection of a two-dimensional boundary. Or perhaps, as the simulation hypothesis cheekily suggests, we're decoding the glitches in reality's source code. Whatever the truth, one thing's certain: the CMB's puzzles won't be solved by tweaking old models. They demand leaps, wild, imaginative bounds into the unknown. So here's the real question: which anomaly keeps you up at night? Is it the eerie silence of missing B-modes, hinting that inflation might be wrong? The spectral distortions that could reveal dark matter's fiery demise? Or the cosmic dipole's drift, whispering of unseen giants beyond our horizon? Drop your favorites in the comments, because the next big breakthrough might not come from a lab or a telescope, but from a curious mind connecting dots nobody else saw. After all, the universe's greatest mysteries often start as faint whispers in the data, waiting for someone bold enough to listen.